In this animation, we're looking at an object moving at constant velocity, and we'll just imagine this thing is an airplane, and it's cruising along and emitting a sinusoidal tone for simplicity, and we see a familiar effect. The wave fronts are piling up in the direction of motion to the right of the plane, and the wave fronts are spread further apart on the left side of the plane opposite the direction of motion. So we remember this is the basic principle behind the Doppler effect for a moving source of sound waves. But in this video, we're going to take the speed of the plane to an extreme value and look at the behavior that emerges when we approach and then break the speed of sound. And just a quick note, of course, airplanes aren't projecting pure sinusoidal tones. They actually produce sound waves primarily due to the compression of the air in front of the plane. So those pressure disturbances are still going to travel as sound waves, even if they aren't sinusoidal. We're just using a sinusoidal tone to make everything easier to visualize. So let's speed the plane up to Mach 0.8, in other words, 80% the speed of sound. We see a definite increase in the compression of wave fronts in front of the plane, and this effect just keeps getting more extreme as we approach the speed of sound. Now we speed up to Mach 1, the speed of sound, and we see something really interesting happening in front of the plane. All the wave fronts are piled up in the same place because the plane is moving the same speed as the sound waves. This pileup of wave fronts is actually what creates the so-called sound barrier, creating extremely high pressure right in front of the plane as it approaches the speed of sound. Now, of course, if the plane has sufficient thrust, it can punch through the sound barrier and the velocity becomes supersonic. So here's what it looks like at Mach 1.2. And now we see the formation of a shock wave propagating behind the airplane. Now remember, this is actually three-dimensional, so that shock wave is actually forming a cone with the plane at the vertex. And this is sometimes called the shock wave cone or the Mach cone. Now as that shock front sweeps along the ground behind the plane, the sudden increase in pressure and subsequent decrease creates a sonic boom. Now unfortunately, or maybe fortunately, I've never experienced a sonic boom from an airplane, but there are more common sources of sound shock waves. For example, the distinct crack of a supersonic bullet, or even the crack of a whip, which occurs when the tip exceeds the speed of sound. Note that this is really good evidence that sonic booms are not due to the engines of a supersonic plane. In fact, it's easy to find pictures of water vapor forming at the shock front off the nose cone of a plane. So we're really talking about sound waves created by the plane slamming into the air. Now let's take a look at what happens to the shock wave cone as the plane moves even faster. This time it's traveling at Mach 2, and we notice the angle of the shock wave cone has narrowed. So there's a velocity dependence to the angle of the shock wave cone, and we can figure that out with a bit of kinematics and trigonometry. Note that all the circular wave fronts are tangential to the shock front. That point is going to be key for our derivation here. Now we label a previous location of the plane at a time of delta t in the past. And this means the distance traveled by the plane during a time of delta t, that's given by the speed of the plane times delta t. That's just distance equals speed times time. And this old picture of the plane over here on the left, that must be the center of a wave front that's now participating in the shock wave cone. And remember that circular wave front is tangential to the surface of the shock wave cone. So now we can label the distance from where the airplane emitted that shock front to the current position of that shock front at the surface of the shock wave cone. Now the distance traveled by that wave front from the time it was emitted to the current time in the picture must be equal to the speed of sound times the amount of time that's gone by. Again, that's just distance equals speed times time, and we're talking about a wave front propagating at the speed of sound. Now finally, given that that wave front is tangential to the surface of the shock wave cone, we can label this angle as 90 degrees. That's the angle between a tangential segment and a radial segment, always 90 degrees. So now we're looking at a right triangle where one leg is given by the speed of sound times delta t and the other leg is given by the speed of the plane times delta t, and we should be able to quickly solve for the angle of the shock wave cone. So we use the sine function for this. The sine of theta is the opposite over the hypotenuse. So we have the speed of sound times delta t over the speed of the plane times delta t, and of course the delta t's are going to cancel out. And we arrive at the formula sine theta is Vs over Vp, where Vs is the speed of sound and Vp is the speed of the plane. And just to wrap things up with a quick example, we can compute the angle of the shockwave cone for this plane flying at a speed of Mach 2. So we have that the speed of the plane is twice the speed of sound. And when we plug into our formula, we have sine theta is the speed of sound over the speed of the plane, but the speed of the plane is twice the speed of sound, and the speed of sound is going to cancel out of that, and we get sine theta equals 1/2. Well, this happens to be a special angle. The angle whose sine is 1/2 is 30 degrees, and we've got the angle of the shockwave cone. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.